Hey, welcome back. We have another video, obviously, which is why you're watching it. We're going to talk about solving systems of linear equations, but we're going to move past the graphing part. That it's fun to graph, kind of fun, I guess, maybe a little bit, and it's useful. We can do it, and we get a really, really solid interpretation of what we're actually doing when we solve systems of linear equations by graphing. That's fantastic. We really grasp the idea, but it's slow. And sometimes it's not effective, especially when our intersection points are fractions. That's a problem. So we're going to develop some more elegant methods on how to solve systems of linear equations without the graphing, with just algebraic techniques. That's one of them. It's called solving systems of linear equations by substitution. I prefaced it in the first video on this 2 videos ago. That one example we did, we sort of did it substitution the first way. Now we're going to learn about how to do it in general. So it really helps though if you have an idea of what's going on. These systems make lines. Where the lines cross is our solution. Where the lines cross, listen carefully, is the one point that's common to both lines. It's the one point where this is key, where the x values are the same for both equations and where the y values are the same for both equations. If you have a point on both lines, the x's are the same. At that one point, the x's are the same for both lines, and the y's are the same for both lines. That's the idea on why substitution works. So one point on both lines, so where they cross, that one point right there, the x's are the same and the y's are the same. That lets you replace pieces of equations with other equations. That's a substitution technique in a nutshell. So here's what we're going to do. How you solve a system of linear equations with substitution is, number one, solve one equation for one variable. Now, I'm gonna ruin the whole suspense for the next lesson. If you don't have one equation solved for one variable already, or if it's not easy to solve, don't use this technique. There's a better way. That's why we deal with elimination technique. Math teachers in general, I know it seems like we try to make your lives harder. We don't. Really, we do. Some do, I guess. But it's not, I don't try to make it harder. What I do is I teach you different techniques to make your lives easier. Because in some cases, substitution method works awesome. In other cases, it really sucks. That's why we develop elimination method. So no matter what, you're going to have a really good method to use. So if you have one equation that's already solved for one variable, or if it's easy to solve for one variable, the substitution method is your best friend. If not, I'm going to show you how to do it with substitution, but we'll have a better method later. Number two, substitute that one equation that's solved for one variable into the other equation that's usually not solved for one variable. So we're going to substitute. Now I'll talk about why we get to as we get there. After that, we're going to solve the resulting equation. So you can have one equation. If you substitute one equation, that variable, into another equation, it's going to remove a variable. That's what's awesome about substitution, is it allows you to remove one of the variables. And then we plug in what we got from that equation into your very first step. It'll all make sense when we go through it. So let's take a look. Number one, that's a system. We actually have 2 lines. Could you graph it? Yes. Would it be fun? No, not really. Not great graphing. This one, yeah, pretty easy. So in the first step here, what we're going to look for is, do you have one equation that's solved for one variable? I don't care what variable it is, and here's why we don't care. All we're looking for at the very end is a point. An ordered pair that has an x and a y that satisfies both of these at the same time. We've already unpacked all that in previous videos. We're looking for where they cross. Where they cross is a point. That point must work in both equations. That's the one point that satisfies both equations. That's why they intersect. Does it really matter whether I find the x first or whether I find the y first? Doesn't even matter. I mean, if I find the y first, I'll just have to plug in to find the x. If I find the x first, I'll have to plug in to find the y. But either way, it doesn't matter what half of the point I find. So I don't care. All we're looking for is one equation solved for one variable. This one's not. Now, it wouldn't be super hard to solve this for x. If we added 3y to both sides, we could solve it for x. But You don't have to solve both of them for a variable. All we have to have is one of them solved for a variable. That's this one. This is what we would say solved for y. The y is all by itself, it's isolated, it's equal to something else. This right here satisfies step number one. It says you have one equation, it's solved for one variable, it looks pretty good. Step number two is where all the magic happens. Here's the idea. I'll say it a couple times, but this is the most in-depth I'm going to get on it, so you got to focus here. What we get to do with systems of equations, with that one point right here, if that one point satisfies both of these equations, that one point is on both of these lines, that one point says my y coordinate for that one point is going to be the same no matter what equation I use. What that means is we're kind of tricking the problem. We say, wait a minute, if I have one point, that y is going to be the same value no matter what equation I plug it into, that point of intersection, that y is going to be the same on both lines. That's the same y. So let's call the y's equal. Let's say that these two y's are the same. Well, they certainly would have to be if it's going to be the point of intersection, the one point that's common to both lines. These y's would have to be the same for us to have one point that's on both lines. That's cool. So if I say those are the same exact y's, which they would have to be to have the same y coordinate, same y coordinate says those y's are the same. Well, then what this y is equal to is what that y has to be equal to. They're the same y's for that one point. All other points, I don't care. I'm not looking for the other points. I'm looking for the point that has the same y coordinates on both lines. Let the y coordinates be the same. That's where the substitution method's power lies. It says, well, wait a second. So I could rewrite the x minus 3y equals 11. That's just my first equation. But if these y's are the same, if this y equals 4x, but these y's are the same, then instead of having 3y, if the y's are the same, it lets you plug what the y is equal to into your other y. It says, well, I have x minus 3y. These y's are identical. So instead of x minus 3y, I could have x minus 3, whatever the y is equal to. That is why we solved for what? That's a lot of y's. That's the reason why we solved for this variable y from step 1, is so that we can let these y's be the same, or the x's in the next one. These y's be the same. Whatever this y equals, equals means equals. Equals means the same. So if I have x minus 3y, but I know what y is, it lets us replace a variable with something else. Now the something else is going to have the different variable in it. That's kind of cool. There's only two variables, right? So if we solve for one variable, it's going to be equal to the opposite variable, x. If you solve for y, you're going to have x's. If you solve for x, you're going to have y's. By replacing your y with what y equals, you're replacing a variable. You're eliminating that variable by plugging in what that variable equals. You're going to be eliminating a variable. That's pretty darn cool. Now that's something we can solve, and this is awesome. So if we do solve this, now that we only have one variable left, and you of course combine some like terms, let's not forget how to do that, okay? Let's remember how to solve some basic equations. We know that if we have one variable, it's pretty nice to solve. You combine some like terms, you either add or subtract your constant term, and your last step is to divide. If we got x equals -1, we have, oh my gosh, we solved for half of our point. I know this. I know that because I set these equal to, when you set your equations equal, when you let one variable y equal the other one, you're forcing that to have the same coordinates there. You say, I want to find the x, listen carefully, if I set my y's equal, I want to find the x variable, the x value, the x coordinate that forces my y coordinate to be the same. That -1 forces your y coordinates to be equal. That's what you're saying here. You're saying, I want to let my y's be the same. Be the same means I can put whatever y equals as equivalent to this y as well. So instead of having this y, I go, no, I don't want that y. I want 4x. They're equal anyway. And it says, let's solve for x now that's going to keep that the same. That's going to force that y coordinate to be equal. That's a really cool idea. I know that -1 is the x coordinate that's going to be the same, or that's going to keep my y coordinates the same. Basically, I'm finding the x coordinate that of our intersection where these lines are going to be the same. That's going to be -1 for x. Now we're only halfway there though. So step number 1, we're solving an equation for a variable. You're going to use that equation in step number 2 to substitute into the opposite equation, one that's not solved for a variable. So we solve one equation for a variable, substitute it into another equation. That's great. That removes a variable. Whatever you're left with, step number 3, solve it. Basically, this is saying I want to find my x value so that it maintains the equality of my y values. You're saying, that's a really fancy way to say it's finding half your point of intersection. That's all it's doing. Well, now we got to find the other point, the other half of your point, your y coordinate. Well, if that's the x value, and I already have something that's solved for y, let's plug that into the equation from step 1. The very same equation, hopefully this makes sense, the very same equation you use to substitute is already solved for your missing variable. Now, think about why that is. Think about why it's always going to be solved for your missing variable. If you have taken this y and replaced it with some x's, your y's are out of the problem. They're out of the problem because you said, I'm replacing these y's with that x, with that 4x. Well, then you're going to be solved for whatever variable you substituted for. You're going to be always solved for that. That means that you can take your x value, plug it in here, and find your y value. That's what I'm talking about in step number 4. So we plug this in. We go, oh, okay. Y equals 4 times my x coordinate, -1. That's -4. Here's a little recap, and then we'll make sure that this actually works for us. So the idea is solve one equation for a variable. If you have a point of intersection, the coordinates of that point must be the same on both lines. That means the x's are equal at that point. The y's are equal at that point. So whatever variable you have solved for, it allows you to substitute by that equality. It says replace this y with whatever this y is equal to. Instead of x minus 3y, it's x minus 3 times 4x. That removes a variable. That's awesome. Solve it, and you've completed half of your point of intersection. That's half the solution. Now, let's take that answer, that half a point, that coordinate, plug it into the equation you actually used to substitute, and it's going to solve the other half for you. That's fantastic. So we plug in -1, we get -4. You complete the other half of your point, and then for goodness sakes, you do not go any further until you check it. Even in your head, that's okay, but check it. X is -1, y is -4. Let's plug that in. If x is -1, it's -1 is -4, y's got to be -4, and it is. Plug it in here. If x is -1, let's see if this works. -1 minus -12. Oh, that's -1 plus 12. That's 11. It does work. That's the one point that satisfies both of these equations. That's so cool. That's the one point that's on both of these lines. They're lines. The one point that's on both of these lines is where these lines intersect. And that's the solution to the system of linear equations. That's awesome. And that's exactly what we do with the substitution method, is we let our variables be equal, and that lets you substitute one expression into the variable of another. That's all there is to it, really. Let's try one more. Well, actually, you know what? Maybe you can do it. I want you to look up there, and I want you to see if you could do that problem right now. Well, do we have one equation solved for one variable? Here, no, that's gonna be nasty. I don't want to solve that. Also, imagine this. Could you imagine trying to solve this with graphing? You got fractions all over the place. You get something that's not solved for y. It's not gonna be fun to graph. And then we're gonna be guessing at what our point is anyway. Not a good way to go about it. So do we have an equation that solves for a variable? No, yes. I don't care whether it's x or y. It doesn't matter as long as you have one equation solved for one variable. What that lets you do is says, well, wait a minute, if these lines are going to intersect, then the point of intersection, at the point of an intersection, the x's are the same for both lines, for both equations. And the y's are the same for both lines, for both equations. So if I have this solved for x, these x's are identical. They have to be the same where they intersect. Let's let them be the same. If they are the same, if you're forcing them to be the same, you're saying, hey, I'm going to call these x's the same. Basically, you're working backwards. You're saying, I'm going to call these x's the same. If I force the x's to be the same, it will find the point that has the same x's on both lines. That is the point of intersection. That's why this works. So we're going to take the equation that's solved for a variable. We're forcing these variables to be the same. We're going to let this x equal this x. If that's the case, it's going to force the points. It's going to force you to find the point where the x's are the same for both lines. That's only one point in the history of both lines. No other point besides intersection is going to have the x values be the same on both lines. And the y values be the same on both lines. You're finding that. So we're going to let this substitute in. So instead of 3x minus 5y, we're taking our equation that's solved for a variable, replacing this variable in the other equation, with what the variable is equal to. If these x's are the same, you have to believe that they're the same on the point of intersection. If these x's are the same, well, this x equals 4y minus 2, and if they're the same, this x also has to equal 4y minus 2. So we let it. So instead of 3x, no, we have 3, what x is equal to? 4y minus 2. Minus 5y sure equals 8, but that gives you something very decent to solve. I want you to think about this for a second. A lot of times in math, we do some stuff that doesn't have relevance yet. Stuff that looked like this from a lot of videos ago, from solving linear equations. Hey, it rings a bell. Why we do this is to get us practice so that when we get here, you don't get lost. So now we can look and go, oh yeah, I'm going to simplify. I'm going to distribute. I'm going to combine some like terms. We're going to add or subtract to get rid of our constant. And last step, we're going to divide. Now, are we done? Is that where we stop? Well, ask yourself the question. Can you graph a point by giving me 1/2 a point? Can you graph a point by saying, it's something, comma 2? You go, well, no, I can't do that. So we figured out that the y-coordinate of the point of intersection is 2. This has said this. By forcing our x's to be equal and saying this x is the same as this x at the point of intersection for both lines, which it is, this is saying, well, the y value that's going to keep those x's the same is 2. That creates half of our point of intersection. Now find the other half. What's great about substitution, the biggest pro about substitution method is that whatever half of the point you're missing is given to you by whatever you substituted. So if you're missing x's, you're going to find it here. If you're missing y's, you're going to find it here. Basically, just plug in what you solved, what you got, what you solved for, plug it in here to the equation you substituted. If you do, looks like 6 to me. We complete the other half of our point. That's the one point in the world that must be on both these lines, and we did it by forcing the variables to be equal. If you force the variables to be equal, it is finding the point that is equal, well, that satisfies both lines, to where these lines are equal. Force the variables to equal, it's forcing the lines to be equal. That's the point of intersection. It's pretty cool. Now you check it. Do not go any further before you check it. So x is 6, y is 2. Let's plug it in. If x is 6, that's 18 minus 5 times 2, that's 10. 18 minus 10 is 8. Oh, it works. It's awesome. Let's check another one. X is 6, y is 2, so let's plug it in here. 4 times 2, that's 8, minus 2 is 6. I know that point is on both lines. If a point is on both lines, it must intersect at that point. That's the point of intersection. That's the solution to our system of linear equations. That's where we're going to stop right now. In the next video, I'm going to show you how to solve these when you don't have one that's automatically solved for x. We're going to go a little quicker because I'm not going to have to teach you what we're actually doing with the steps. They're going to be exactly the same. We're just going to go a little bit further and talk about how you get down to this point if it's not given to you. I'll also start talking about, you know how I teach by this point. I teach you ahead of where we're at, so to preface certain information. I'll start teaching you why we're going to have a different method. So we're going to have some really weird, crappy looking problems in the next video that we're going to do with substitution method to illustrate why we're going to have a different method, because it's going to suck. So I'll see you for the next sucky video on when we talk about substitution method part 2. Have a great day.